This truly is one of my favorite sessions of the whole 2 days, and I've really been looking forward to this. So I've got Matt, Gaston, and Martial just really trying to help us get beyond the buzzwords on what's going to be happening with AI engineering. Now, I've just set a high bar in terms of coming in. But let's welcome them and get them started out.
Hello, everyone. My name is Matt Gaston. I lead the Emerging Technology Center here at the Software Engineering Institute. We're very lucky today to have Dean Martial Hebert with us for a conversation, a future conversation on defining AI engineering. We actually heard this morning from Paul and Michael and Tom a lot of use of this phrase, AI engineering, and hopefully over the next 34 and a half minutes, we'll get to talk about what we mean by AI engineering and why it's important, hopefully, to all of you. So first, I'd like to introduce Martial. We were just discussing, Martial is the, I think, officially 5th or 6th Dean of the School of Computer Science.
We're still debating that. We have to come up with the protocol.
There's probably a probability distribution over that. So Martial is newly named Dean of the School of Computer Science here at CMU. Again, I think 5th full-time Dean of the school. For those of you that might not be that familiar with the School of Computer Science, I like to brag about it. I'm sure Martial would too if he was to talk about it. But
feel free to brag.
World-renowned, ranked -- in computer science in the world. To be fair to some of our colleagues in the room, tied with MIT and other places. And recently also designated #1 in artificial intelligence, I believe for graduate programs. And we also added very recently a bachelor's degree in artificial intelligence here at CMU. And to give you a size of a sense of the scope of computer science here, there are 7 academic departments within the school, 270 faculty, which I find amazing, and 2,300 students in the School of Computer Science here at CMU. So a little bit about Martial. Again, just named Dean in August of this year. Maybe we can congratulate Martial on being named Dean. But before being named Dean in August, Martial was the head of the Robotics Institute here at CMU, and he's actually been on the faculty for 35 years. He's a recognized world expert in computer vision. And I like this fact, that when he joined the faculty, he joined a group called the Autonomous Land Vehicles Program. That's 35 years ago, I think long before self-driving cars were fashionable in the streets of Pittsburgh and other cities around the country.
It took a while to get there.
Yeah. So I'm very honored, very grateful to Martial for being here today and joining us, and I'm very honored to be up here with him.
Thank you.
So the panel, the discussion is about AI engineering. I think we should start maybe one step back from there. And since I'm sitting here with the Dean of Computer Science at CMU, I thought we would just start with the question of AI. How does CMU, how do you in the School of Computer Science just think of AI in general before we dive in on the engineering topic?
Yeah, so if we look at the advent of AI in the past few years, we have several factors that basically conspired to make this happen. One is, of course, the availability of massive amount of data, and not only massive amount of data, but the ability to store, process, curate that data. The availability of massive amount of computing, and by that I don't mean just online computing, but also cloud computing, which enabled training at a scale that was not possible before. And finally, the development of new techniques, new algorithmic techniques that conspired with the data and the computing to enable completely new AI approaches. The other aspect that is really accelerating this process is the convergence of AI tools with actual applications. As you pointed out, the AI research started a long time ago, depending where you point exactly, it's maybe 50 years ago. For a very long time, we were developing individual tools, search system, reasoning system, etc., that were doing interesting things on isolated data. Now, I think over the past few years, we've really reached a tipping point where those systems actually are applicable to actual domains. And in fact, now I think we're entering a new phase where it's not just AI used as a toolbox of interesting tools that can be used to help solve problems. It's actually AI merging with other fields to create completely new fields. And what that does is to create new research challenges, completely new research lines that did not exist before. So, for example, we have a new, we're experts at creating new educational program, new degree program. We do this on a regular basis. There is a new degree program, for example, on essentially AI and robotics for automated scientific discovery, okay? This is an example here where it's not just AI used as tools to make things a little bit faster, but it's actually AI melded with another domain to create a completely new discipline with its own challenges, its own approaches, even its own language. So I think that's kind of the evolution that we're seeing now.
Okay, great. One follow-up, because I always feel like we can get caught up in the terminology here. You mentioned search and reasoning and other aspects of AI. I find that in some circles, AI and machine learning get used interchangeably. I think of one as part of the other, but I thought you might have comments on that.
Now you're going to make me angry. You were asking the question as to how at the school in particular we made progress in AI. One of the key points is to take a very broad and comprehensive view of what we mean by AI. As soon as we narrow it down to one component, no matter how successful at the moment, we basically lose. So machine learning, deep learning within that, has been a tremendously successful set of tools, made tremendous progress over the last few years. But the key to actually develop real systems, not just, showing some performance on some data, but actually developing real systems, is to view AI as encompassing the entire chain, from the acquiring the data, the sensing, etc., to the manipulating that data, computing, storing, etc., to the machine learning, to the decision-making, things like game theory, reasoning, search, etc., all the way to human interaction and other issues in autonomy. And we have to include the entire vision of AI to make progress. So that was a long answer to your question as to why equating AI with machine learning is a bad idea.
Okay, thank you for that. You talked here just now about taking a broad view of AI and building whole systems that incorporate AI. So that's a nice segue. And I'll just give you the open-ended opportunity to tell me what you think AI engineering means. We heard this term used a lot this morning and through the course of the day. What does that mean to you?
Well, you answered the question in your question. It's basically, to me, and people may have different definitions, but to me, it's going from this progress in each individual tool, okay, to actual systems that can be trusted, that have predictable performance, okay, and that can act and operate in the environment in which they are intended to operate. And the point we're in now is that the progress in individual technology is accelerating. You mentioned deep learning, for example. There are many other examples, progress in computer vision and other things that we involved here. But now the issue is to be able to take that progress and actually migrate it into actual systems. So to take an example that I know very well from my own discipline, I work in computer vision and robotics. And if you look at the performance or the stated performance of computer vision approaches and compare that with the performance in the context of actual robotic systems, like manipulation systems, self-driving and all that, there is a huge gap between the two. And the reason why there is the huge gap is because we don't have the engineering tools and the processes and the best practices on how to go from one to the other. It's a little bit like you have a toolbox with amazing tools, and you don't quite know how to use them, right?
Interesting. Okay, good. Let's go a little bit deeper on that same theme. We're using AI engineering as if it's an eye towards the future, right? We're thinking about, AI has made so much progress, and organizations, the DoD and other organizations like that, are starting to adopt, acquire, integrate, use these AI capabilities. How does AI engineering sort of introduce new challenges compared to more traditional engineering?
Right. Right. So the kind of, to start by stating the obvious, is that AI systems depend in large part on data. So what that means is that if you want to prove or evaluate the performance of a system, the performance of the system does not depend just on the correctness of the software or the specification of the hardware. It depends on the data that was used to train that system, okay? Worse than that, that data is quite often, and in most cases actually, is not static. It's going to evolve over time. How do you characterize the performance of the system as the data changes over time, right? That drives the performance of the system. Another issue is the kind of sensitivity analysis or perturbation analysis that you do in a typical engineered system, right? So in a typical engineered system, not that I want to pretend to be an engineer, but so let me, sorry if I simplify things a little bit, but you basically take your input parameters, right? And you're going to perturbate those input parameters and see how the performance changes, okay? What does it mean to perturbate the data, right? What does it mean to say, okay, the data that I'm going to observe now in this current environment is this far from my training data? You know, what exactly does that mean? How do you characterize the sensitivity of the system to deviation from the data that it was trained on? All those kind of issues are specific to AI system, in large part. And not only they are specific, but they are critical to AI system. And we don't have the right tools yet, I think, to do this kind of thing. That's where some of the research is. Now, the situation is even more complicated when now we insert the human in the loop. I like to say quite often, you know, that a lot of the research we do in AI and robotics in particular is not about the AI system or the robotic system. It's about the people, how people behave, how we can predict their behavior, how we can characterize the behavior. That is another component that is different from maybe more classical engineered system.
One of the challenges I hear a lot when it comes to the people involved in either using or interacting with these types of systems is either explainability or interpretability. Yeah. Can you share a little bit more on where we are with those as concepts, yes, both scientifically and in the engineering world?
Yeah, so there's a lot of work on explainability that has been in large part motivated by the advent of black box technique, as we call them, like deep learning technique, where you have input, output, and very little understanding, or describability, explainability of what's going on in between. So there's a lot of programs, there's the big DARPA, explainable AI program, and so forth. That is, of course, important to be able to have people interact with the system and trust the system. But one thing that I want to mention, there's been a big move toward explainability. It's a very popular topic, many articles about that. But now we're stepping back a little bit because it's really hard and asking the question, do we need explainability, or perhaps all we need really is predictability? All right? So if I walk off the stage here and start working over there, I'm not going to bump into anything. I'm sober today, so I'm not going to bump into anything, okay? I can't explain to you how I did that. I cannot explain the process whereby I got photons in my eyes and made that decision, okay? But I'm pretty predictable. And you know that I'm predictable too. You don't need to hold my hand to walk there, okay? And this is an important concept, and there's a lot of work emerging on concepts of predictability, legibility. In other words, understanding what the system is trying to do, which is very different than explainability. And it's maybe actually a more achievable goal. Right? And not only more achievable, but maybe explainability is in many cases not necessary, not really what you want to look at.
Okay. Now, this is the Software Engineering Institute's research review. And by my count, much of AI systems is built with software, I think.
Yeah.
We know a lot about good software engineering practices. How does AI challenge software engineering in particular? And why can't it just be a solved problem, since we know how to do software engineering?
Yes. So part of the answer, at least part of the answer, has to do with what I started with earlier in defining the difficulty in AI engineering, which is the dependence on data. Mm-hmm. Okay? That is, again, has nothing to do with the correctness of the software in the traditional engineering sense. The adequation of the software with the specification, which is another aspect of software engineering. It has to do with how to validate that data, how to communicate it, how to share it, how to format it, etc. As a matter of fact, there is an RFI, request for information, from the government out right now on all of those topics, basically asking the question in this age of all the systems depending on AI, how should we represent data? And especially from a competitive standpoint, how should we represent it in a way that can be shared across different interested parties, for example, across different self-driving car companies, while retaining competitive information and while preserving privacy. So there's a whole host of issues that have to do with just the data, not even the software,
right,
that I think are very specific there. Another aspect has to do with when I was saying a broad view of AI, you can think of this in the middle, you have the thinking, right? And on the left, this is not a political statement, by the way, but on the left, you have the sensing, and on the right, you have the acting, okay? And you have to think to include in the AI engineering, not just the thinking, which is roughly speaking software, but also the sensing and the acquiring the data. And there is a rapidly expanding field of research related to IoT and various types of sensing that looks at the problem, how can I acquire the data that I actually need for my AI? So those are kind of things that are actually in some cases very far from what you would think purely as software, right?
Sure.
But have to be integrated in the thinking.
So two follow-ons maybe to that discussion. You just said it. How do you acquire the data you need for your AI system? How do you do that? How do you know? How do you know that you have the right data, that the data you have is sufficient or good or not riddled with problems? How do you know?
Yeah, you look at me like you have solved the problem or something, but I have not.
I'm hoping.
No, this is again the kind of problem that I referred earlier as this sensitivity analysis, if you will, that kind of thing, where you want to be able to analyze the data in this fashion. This is still in large part an open problem. If you look at the self-driving, for example, a lot of work on issues of data coverage, for example. To ensure that you cover enough of the environmental condition and so forth. So that is a major challenge.
Okay. Changing gears, there's companies out there that have been doing substantial amounts of AI development and AI deployment into their systems, into the way they work, the way they make money, and the government in pockets has been doing AI for a while, but is really pushing to adopt more and more. Do you see any major differences between what's been going on in the commercial world and the challenges that the government has to face from an AI engineering perspective specifically?
Okay, by government, you mean defense in particular?
Defense in particular.
Okay. One key difference is the level of structure in the environment and in the problem. If you have a commercial problem, you typically have the opportunity to shape the problem, to shape the environment, to shape the scenario, to shape the constraints. Even if in what people think of as free-form self-driving, take a car and it's getting and it's going to drive no matter where. That doesn't exist. That's not going to exist for a very, very long time. Maybe it will never exist. What does exist is companies that have plans for being able to deploy self-driving cars in a controlled fashion. In other words, they know which routes or sets of routes or environment the car is going to drive in. They can even control, in the case of Uber, for example, they can even control when they allow a self-driving car to drive or not based on weather conditions. Mm-hmm. So in other words, even in that case, that looks like kind of a very unconstrained AI system, it is actually constrained in the commercial world. In the defense world now, you have the opposite problem, where the environment is unstructured, much more unpredictable, okay? Changing rapidly, etc. So in other words, you don't have as much of a luxury of constraining the problem or the environment. And that's a central difference between the two types of application, in my opinion.
I want to ask a question along the lines of how much harder is it? Is it hopeless in those environments? Surely there are methods or techniques that many researchers are working on that will help with these problems.
So, of course not. It's not hopeless.
I knew that.
If we say that, we all go home. I mean, we give up. No, absolutely not. One of the key things that we don't know how to do currently in AI, and specifically AI engineering, I believe, is to have systems that are able to themselves understand their own limitation. So in other words, it's okay for a system to encounter a situation that it cannot handle because it's completely outside of the envelope that it has been designed for or trained for. The problem is that it has to recognize that it cannot handle that situation and then report that back and maybe take action. That sounds like a simple thing, right? To recognize that I don't know what to do. In fact, it's a really, really hard thing. And there are entire programs now. There's a DARPA program on competency-aware systems. Okay, there's a ONR program on self-aware system. Okay, those kind of things, and they all point in the same direction. You cannot guarantee that in such an unstructured environment, the system, the AI, is going to be able to handle the situation in all cases. By definition, you can't guarantee that because it's unstructured. But what you have to somehow guarantee is that the system will recognize when it's not able to make a sound decision. And that's still very, very hard.
Don't feel free to not answer this question, but I'm wondering if you have an example. I'm wondering if you have an example of such a system that's been built and used. I actually heard a story in the past about the self-driving vehicles here at CMU that participated in the DARPA Grand Challenges, the robotics Grand Challenges, and how they had a sub-control system that when it didn't know what to do, when it couldn't recognize the situation, it just did something small and random to get it out of that situation. I don't know if you have another example of something like that.
Yeah, well, in my group, we developed a introspection system for drone, for example, that would basically learn to map the input images coming at it to how well it would generate trajectories, right? And at runtime online, it would then have an evaluation, if you will, of how well it might do. So this is implementing the silly analogy that if you're driving and suddenly you're surrounded by fog, right, you're going to slow down, right? Why? Because you have immediate introspective assessment that your visual system is impaired and you have to slow down. So it's implementing basically that kind of behavior. The difficulty is to be able to implement it in a way that is general, right? That is not, something that is a one-time, hack or something for this particular system. So to have a general approach to implement that. That also points to, if I may add to that, that also points to another difficulty that is unique to complex AI system, which is the error metric, if you will, that is used to evaluate the system. So in this example of the flying drone, we could do the following. We could look at the vision system and ask the question, how well is the vision system reconstructing the 3D world? Okay? And then say, well, if it looks like it's not going to do a good job, then I have degraded performance. The problem is, how do I measure how well it's reconstructing the 3D world? Well, natural answer would be what? What would you say?
Have a model of the world.
Well, yeah, but with respect, you compare it and see the accuracy of the depth, right? So here it's better because it's 3 millimeter accuracy. Here it's better because it's 2 millimeter. Do I care if it's 2 millimeter instead of 3 millimeter? No. The only thing I care is that it flies correctly and it avoids the obstacles correctly. So another example is in semantic segmentation. If you don't know what semantic segmentation means, in computer vision, that's the process of labeling pixels as to what they are. So you would label these pixels as a table, this pixel as a glass, bottle, etc. This is an extremely important process, for example, for driving, right? You want to understand what's around. Okay. If you look at the vision system itself, the error metric that is used for that vision system tries to minimize the number of pixels that are mislabeled. So in other words, it tries to label all the pixels as correctly as possible. Is there one application in the universe where you need every pixel in the image labeled correctly? Of course not. So in other words, the vision system is using the wrong error metric, and it's using one that is harder than the one that we need to actually solve the task. So this is the idea of having a task-based task-based design of the entire chain of the AI system, which is something that we know how to do for simple tasks like flying or grasping, but we don't know how to do for complex tasks. Okay, and the problem, coming back to your question about introspection and knowing where it fails and all that, is that you want to know this with respect to the entire task, right? You don't care if it labels fewer pixels or not. You want to know if it's going to carry out the task correctly.
Sure. I hope we're capturing notes, because I'm hearing a lot of design patterns and things like that we need to promote out there into the world of people that are building AI systems. I will open it to the floor for any questions, so I'm hoping not everyone is sleepy after lunch. I'm going to ask one more series of questions from my perspective, but then there'll be a few minutes for questions from the floor. So again, Software Engineering Institute, we know a lot about software engineering. We also know a lot about cybersecurity. And so I feel like in a conversation about AI engineering, we have to bring in this idea of security. My sense, my intuition, and in fact, I know that AI introduces some interesting risks, vulnerabilities into systems. Can you give us a perspective on that?
Yes, so the first thing, and in fact, we did not mention that in answer to your question about government application, but of course there is the adversarial aspects,
yes.
which are far more prevalent in those applications, and that goes, of course, to the security aspect. This is also somewhat connected to the explainability, because if you look at what keeps some people up at night these days, is those examples that many people have seen of deep learning system that can be fooled actually relatively easily, right, adversarially. And part of the reason, the complexity here is the lack of explainability. Right? You have basically a black box, and it's very difficult to explain basically how why this attack was successful. It's also very difficult to now modify the system so that attacks are not successful. So there's certainly a big challenge here. On the upstream now, there is the issue, again, going back to the data, to sound like a broken record, but then there is the issue of, and this goes back to my sensitivity analogy, right? This goes back to the integrity of the data and how to prevent the data to be deliberately corrupted. See, if we make progress, this is the paradoxical thing, right? If we make progress on modeling this data sensitivity that I was speaking of, then we also make progress in being able to corrupt the data, because now we know how the performance are going to change with certain changes in the data. So now you have another line of attack, basically.
Sure.
Sorry to be a downer.
No. So you talked about error metrics and sort of the evaluations of these systems when they're being either trained or built. Is there something that can be done at that error metric definition time, right, at the design of that metric, to bring robustness or security into the system, right? Instead of just pushing after accuracy, which is what most of the research in computer vision does, right? It goes for accuracy. Can it also be trained for robustness?
Yeah, so that was the distinction that I was making with my example on introspection, right? In some sense, and this is this business of going from the individual pieces. So the individual pieces you can measure based on their individual accuracy. The problem is that does not necessarily translate to the robustness of the overall system. So in an ideal world, what we want to do is to have a metric that truly captures the task that we want to achieve, and to be able to backpropagate basically this metric throughout the entire system. That's what we would like to do ideally. And again, that actually works for some systems. There's a lot of work, for example, on those grasping system, right? You have a robot that grasps, and the task here is easily measurable. Either it grasped or it did not. You can even have some stability metric, it grasped stably or not, And that's easy to measure, right? And so you can backpropagate that through the system. For more complex tasks, which are the ones that we typically want, like navigation and things like this, you can't do that.
Okay, I certainly have more questions, but I wanted to open it to the floor. If anyone has a question, I see some fingers pointing. Someone else guided, I'm not going to pick.
Hi, so I work for the Army, and one of our big challenges is trying to get systems fielded, and we have to go through our testing community. And our testing community, they very much want to lock down software. So anytime software changes or anything like that, they want us to go back through testing. So if we have AI systems that are constantly evolving, or even like you were mentioning earlier, we have new data sets that come in, has there been any work in terms of how we can move through that testing process faster, or how we can validate these systems quicker so that, they're not constantly being stuck, being evaluated and tested?
Well, there's a kind of a short-term answer to this. I don't know about faster, by the way, but I think maybe there's a short-term answer to this and a longer-term answer to this. The short-term answer is to not just look at the software part, as we were discussing earlier, but look at the data part as well. So in other words, it's not just evaluating the software or freezing the software, it's also evaluating the data and freezing the data. And they have to go together now. The longer-term answer is to develop the right tools, as I described earlier, to understand the sensitivity to data. So now you can, instead of having to apparently retest the system every time the data changes, right? That you can now predict what the changes in performance of the systems are going to be. Right?
So how do you explain the quality of the onboard software for hummingbirds?
I don't. I don't. Part of the answer goes back to that task-based design. Part of the answer. Now, I cannot give you a biological answer or anything like this, but at least at a high level, part of the answer is that the entire system is designed to do one thing, not to do scene understanding, not to do 3D reconstruction or anything like that. It's designed to do one thing. And that's, I think, eventually part of the secret sauce to have really powerful AI system. We're still at the stage, in my semantic labeling example, we're still at the stage where we have components that are actually way too complicated. They do probably way too much for what we actually need to do. And maybe, I don't know, 10, 50 years or 100 years from now, we'll be amazed at how complicated we made things, I think, is what's going to happen.
100 years from now is a lot more AI research under our belts.
Yes,
right?
yes.
We have time for one more, or I can go back to the questions that I have. Anyone in the audience? Okay. I think this is an amazing group assembled in front of us, right? Our sponsors and customers in DoD and collaborators and everyone else. Very open-ended. What recommendations would you make, right? As the dean now of computer science here at CMU, what recommendations do you make to this community as they think about AI engineering and how to realize these capabilities for mission?
Yeah, so I think there's a short-term and long-term answer. Let me give the long-term answer. Is that there are fundamental research elements that need to be addressed for AI engineering to work, and especially to be able to build the complex AI system of the future. We talked a lot about this evaluation, self-awareness, and et cetera. I emphasize again, those things are not a matter of designing systems a little bit better. This requires completely new tools for this. We need to invest in that, and we need to pursue that line of research, and as well as the one we indicated in terms of predictability of systems, etc. That is the only way we're going to be able to address this problem of test and evaluation of the system and get around that the current approaches.
Okay, so we heard a lot. The data is important. Interpretability or maybe predictability of these systems is very important. We must do task-based design and have the right metrics that we use to evaluate these systems. They're not just individual things. They can't be overly optimized for one task. It's about integrating into this larger whole. So I think a lot to think about, maybe more problems than answers right now. And that gets to your final point, which is there's certainly a need for investment in the research behind this idea of AI engineering. So with that, I think we're out of time. Martial, I want to thank you so much for joining us today. This was a lot of fun.
Thank you. Thank you.